welcome to another AQA AS chemistry video. This is the second part of the video for the inorganic chemistry series I'm going to be doing for AS chemistry, of course. And yeah, we're going to go straight into it. So the last video was about the periodic table, and I'm going to be going through the trends in the periodic table. So atomic radius. So there are key trends in atomic radius as we go across the periods and when we go down groups. So periodic trends, right? So if we're talking about the atomic radius and we're talking about the periodic trend, the atomic radius actually decreases across a period. Let me actually get my periodic table to dive with me. Alright, cool. Yes. Got this here. So as you go, so atomic radius decreases across a period, and this is because the number of protons in the nucleus increases, or you can call it the nuclear charge increases across the period. As you add protons, you also add electrons, but these, as I said before, when we're talking about going across the period in the previous video, check out the previous video. Electrons across a period are added to the same valence. So the valence electrons in a period are on the same energy level. So what that means is that as you add protons, you add electrons, but these are all being added to the same shell, so it doesn't affect the radius. So as we go across this period, right, we would expect the atomic radius to decrease. The reason for, as I said before, the nuclear charge increasing, as you can clearly see here, 11, 12. The nuclear charge, actually you can just clearly see from the AR really, but the nuclear charge increase, well, either way, protons is the one that affects it anyway. The neutrons don't do anything. Yeah, atomic number increases. Atomic number, nuclear charge. If they ever ask this in the exam, you can say atomic number, nuclear charge. If certain questions may require you to specify charge density, but don't worry too much about that. Actually, charge density is actually quite important to this. Charge density is more to do with the fact that it's you have a high nuclear charge for a small molecule. So if you have a high nuclear charge and a small molecule, or small atomic radius, you should say. It doesn't have to be necessarily a molecule. It could be an atom or an ion, really. It's usually referred to with ions or atoms. But if you have a high nuclear charge and a small atomic radius, that's considered to have a high charge density. It's very dense with high positive charge overall, or and something with a high charge density is considered to be quite electropositive, I say, or high electronegativity usually. Yeah, very strong positive charge, very electronegative. In terms of the fact that you can attract negative charge. But anyway, I kind of went a bit off topic there, but as you go across the period, right, the nuclear charge increases and the electrons are all in the same energy level. So because of that, the nuclear charge, the effect, that positive effect of the nuclear charge is more strongly felt. So the electrostatic attraction between the nucleus and the outermost electrons would increase, because think about it like this, right? Let's say, I'm not going to use pencil for this. I'm not going to use this, but if I was to use, let's say, let's go down here, right? Sketch, right? So I said, some people may just get this, but for people that just don't get this, what I mean is that the electrons are all the same distance from one another, even as you go across the period, because sodium, right? Sodium here, positive charge, that. It's in period 3, right? You know all the electrons are gonna be in this energy level here in period in the across period 3. They're all gonna be in this energy level here. So the electrons are all the same. Essentially, the nucleus is the same distance away from the electrons, whether it's here, 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 here. So sodium would have a nuclear charge of what? 11. But magnesium, is the energy levels are all the same distance from one another. From the nucleus, if you're talking about period 3, right? Period 3 is the same distance from the nucleus as other compounds. However, the reason why it would decrease, theoretically it would be the same, but technically it's not. I'll explain why, right? So idealistically, right, they're the same distance from one another, but it'll be pulled in more. So overall, it will be it will get smaller as you go across the period, right? So let me just stop talking and just show you. maybe messing this up in terms of the way I'm explaining it, but I promise you it will make sense, right? If you're talking about if you're talking about it technically, right? Technically, this is the period freeze, right? Let's just forget about the charge, the attraction and all of that for a second, right? This is the same. This period freeze is the same distance away from the nucleus in magnesium as it is in sodium, right? But remember, the nuclear charge in this is 11, and the nuclear charge in this is 12. This has a 1 plus, or this has a higher nuclear charge by 1. Because there's 11 protons here but 12 in here. So since they're the same distance away from one another, the effect, and there's the same shielding, there's a stronger electrostatic attraction between the outermost electrons in magnesium, between the outermost electrons in magnesium and the nucleus in magnesium, compared to sodium and the outermost electron, between the nucleus of sodium and the outermost electron in sodium, because they're the same distance away from one another, but this has a stronger positive charge, and they're all the same distance from one another. So therefore, this would pull in, because there's a stronger electrostatic attraction between magnesium, between the magnesium nucleus and the outermost electron. This has a strong electrostatic attraction which pulls it in, further pulls the outermost electrons or the outer shell further inwards than the sodium. So in reality, the magnesium would have a smaller size, or smaller atomic radius compared to sodium. And as you go across period 3, aluminium, silicon, phosphorus, sulfur, chlorine, ideally argon would have the smallest atomic radius because it has the highest nuclear charge, and the electrons are all in the same energy level. So they're the same distance from the nucleus, but it would have such a strong nuclear charge, it would have the strongest electrostatic attraction between the nucleus and the outermost shell, or the outermost electrons in that shell, pulling it in the greatest, causing it to have the smallest atomic radius. Hopefully that made sense. But yeah, kind of went through that. Kind of went off on a tangent there, maybe a little bit. So period example, in period 3, sulfur has a smaller atomic radius than phosphorus. So sulfur has a smaller atomic radius than phosphorus. Yes. Sulfur has one more electron. So it has one more electron. The electron increases, yes, but as I said before, this still only fills up the same shell, which is the same 3p shell as phosphorus, so the radius isn't affected. But sulfur has one more proton than phosphorus, and this doesn't affect the radius. Sulfur has one more electron, but still only fills up the same shell, the same orbital, or same energy level on the 3p orbital as phosphorus. So the radius isn't affected because of that. The radius isn't affected because they're on the same shell, but sulfur has one more proton than phosphorus, so that affects the radius. I think I've already made it pretty clear. I don't want to use any more analogies, right? These are on the same. Think of it as a circle, right? The electrons are on the same shell, so it doesn't affect the radius from the nucleus. If they're on the same shell if something's on the same line on a circumference of a circle, right, it's going to be the same distance from the radius, right? But if we increase the positive charge of this nucleus, the electrostatic attraction would increase, and that pulls this shell close towards the nucleus, and that's all that's happening, right? It doesn't matter how many electrons you add to this shell, because they're all going to be on the same shell, and it doesn't affect it. It has the same shielding, because this partner would be the first energy level and the second energy level will have the exact same shielding as one another. So the only thing that would affect it is the nuclear charge, which affects the electrostatic attraction and that pull. All right, cool. I'm going to stop talking about that now, I promise. So sulfur has one more proton than phosphorus. This does affect the radius. Sulfur has a greater nuclear charge because of having one more proton, and this pulls the electrons closer, and this means atomic radius is smaller. Group trend. So atomic radius would increase down a group, and this is because the number of electron shells increases down a group, and each subsequent electron shell is further from the nucleus, and this effect outweighs the increase in proton number down the group. All right, so in short, basically it's, sorry about that. as you go down the group, the nuclear, or the atomic radius would increase, because the nuclear charge may be increasing, yes, but you're increasing the number of shells, right? There's not the electrons aren't on the same energy level anymore. They're not on the same shell. You've gone, as you go down the group, you increase the number of electron shells. So group 1, but on period 2, would have 2 energy levels. Same number of electrons outermost shell, but it's on group 2, but compared to sodium, which is on period 3, but in the group 1, period 3, right, it has an extra, there's 3 energy levels. Group potassium, 4 energy levels, rubidium, 5 energy levels. So the number of energy levels has increased now. The shielding has increased, the distance from the nucleus has increased. All these things would have, though the nuclear charge the nuclear charge is increasing, the number of energy levels, the shielding, the distance, that would all make the electrostatic attraction much weaker in general. So therefore, yeah, and I mean that overall you have, as you go down the group, nuclear charge, as you go down the group, the atomic radius would increase down the group, and vice versa if it's going up a group, right? So group example. So in group 2, magnesium has a larger radius than beryllium. Magnesium, as you would expect, is lower down the group than beryllium, has an extra energy level shell. So magnesium has more electrons than beryllium, and they occupy an additional electron shell, and the extra electron shell is further from the nucleus. So the atomic radius is larger, right? Beryllium, what's in group 2, right? Beryllium has 4 electrons. There's only 2 electron shells for beryllium, 3 for magnesium. As you can see here, this would be much smaller because there's less energy levels, or less electron shells, and less shielding, of course. And that's it. That's pretty straightforward. Yeah. So far we're talking about atomic radius. The trends in atomic radius across the period. The atomic radius would decrease across the period, and there's an increase in nuclear charge. Down the group, there's an increase in atomic radius as you go down the group, and there's an increasing valence electron orbital size as you go down the group. So, down the group? Yeah, down the group. All right. So, ionization energies. We see trends in ionization energy across periods and down the groups of the periodic table. So now we're talking about ionization energies, right? And in case people don't know what ionization energy is, it's just the energy needed to remove the outermost electron from an atom or ion, which is the energy required to remove that electron. That's all it is, right? Alright, so now I'm going to be talking about the trends, right? So the periodic trend for ionization energy is that ionization energy increases as you go along a group, and it's for the same reasoning as I said before with when I talk about size of periodic trends, is that electrostatic attraction that increases because the nuclear charge increases, but the electrons are on the same energy level. The valence electrons are on the same valence shell. By the way, we call the outermost electron, that valence electrons occupy the valence shell. That outermost shell is called the valence shell. Those because they have the first electrons to react. So, nuclear charge increases, but electrons are on the same valence shell. So therefore, there's a stronger, as you go across the periods, right? As you go across the period, electrostatic attraction between the nucleus, and this is the most important part. I have to say that I don't think you have to say the word electrostatic, but at least saying the word attraction, right? There's a stronger I always say electrostatic, but there's a stronger electrostatic attraction between the nucleus and the outermost electrons or valence electrons as you go across the period, because nuclear charge increases for electrons that are in the same energy level, and therefore that means that there's as you go across, generally as you go across the period, the general trend is that ionization energy um, increases. However, I don't know if it's going to go through it in this video. There are two examples that generally that's the trend, but there are two anomalies, and they have reasons for those anomalies, and the anomalies are between magnesium and aluminium. Uh, the ionization energy decrease between magnesium and aluminium, but and the other one is between phosphorus and sulfur. But generally, apart from that, as you go across the period, the nuclear charge, sorry, not nuclear charge, the ionization energy increases. But between magnesium and aluminium and phosphorus and sulfur, it actually decreases for that reason. But I don't know if I'll go through that in this video, but I'll definitely go. Because I'm using the Seneca model to go through it, but there are reasons for why that happens. So periodic example. In period 3, chlorine has a greater nuclear charge than sulfur because it has sulfur has. I'm talking about ionization energies now. Chlorine, yeah, sorry, yeah, I said, yeah. Chlorine has a in period 3, chlorine has a greater nuclear charge than sulfur because it has a greater proton number or greater yeah, that's what it means anyway. In period 3, chlorine has a greater nuclear charge than sulfur because it has a greater proton number. So the electrostatic charge between electrons and the nucleus in chlorine will be greater. So the ionization energy is greater. Yeah, that's pretty self-explanatory. Group trend. Ionization energy decreases down the group, and it's for the same reason when I talk about size. Nuclear charge may increase, but the number of electron shells also increases, and it's also increased electron shielding. So overall, there's a weaker electrostatic attraction between the nucleus and the outermost electrons. As I said before, so this is because the outer electrons is further from the nucleus down the group, and the electrostatic attraction of the outer electron to the nucleus decreases down the group. Yeah. And group example, in group 2, magnesium is below beryllium. Magnesium fills up an electron. Sorry, magnesium fills up an extra electron shell than beryllium. This means an electron is further from the nucleus of magnesium, and so the electrostatic attraction is less. So the ionization energy of magnesium is lower than beryllium. So as you go down, in group 2, beryllium would have the highest ionization energy, and radium would have the weakest. And that kind of plays into hand why, for certain reactions, ionization is up here, but as I said, for certain reactions, for example with water, right? These heavy metals here would react so greatly because it's the ionization energy is so weak. It's so easy to remove that electron shell. So easy to remove that electron shell. So just simply dipping it in water is enough energy to, when the water reacts with it, is enough to do it. So that's how it has such an explosive reaction, such a rapid reaction. Whereas with beryllium, it's the ionization energy is a much higher, requires much more energy for it to remove that electron, and that's you know, that's why it's important to know these trends. Melting point. So there are clear trends in melting points across periods and down groups in the periodic table. We look at period 3 to see the trend. So the structure and melting point. So for metals, we already know the greater number of valence electrons, the greater the melting point. For covalent compounds, molecular solids have low melting points, and giant covalent structures have relatively high melting points. And then, obviously, molecular compounds wouldn't have a very low melting point because they have very weak van-der-Waals molecular forces. So, period trend. As you go, this is one of the things that you also need to know. Remember, there's 3 things you need to know when you're talking about in inorganic chemistry. When you're talking about properties, right? The physical properties are I say some of them are chemical, but one of the physical properties are like melting points and all of that. But the other two, I said they're more chemical features. If I'm being honest, the 2 chemical features you need to know that are no, ionization energy is more of a chemical feature. If I'm being honest, but in case I'm wrong, but the 3 things you need to know about are the 3 features you need to know are ionization energy, size, and melting point. I've already covered the reasons and the different the reasons and the trends. The trends, as I should say. I already covered the trends and the reasons for the size and the ionization energy, and I'm going to be going through the melting points. And as you go across the period, it's actually a range of different melting points. There is a trend. There is a trend, but there are reasons for it because they don't have the same type of bonding necessarily. I say there's more of a range in type of bonding, right? So as you move along the period, you go from metals to giant covalent structures to molecular solids. So metals, so metals, right, to giant covalent structures to molecular solids. And that's so generally what you would see is that there's a slight increase. There's generally a high melting point because of the metals as you go from group 1 to group 3 metals. And then it goes to silicon, which has covalent bonding, which is very strong covalent bonding. You see carbon, silicon, these kind of giant covalent structures. And then so that has the highest melting point. And then you go down to molecular solids, so phosphorus, sulfur, chlorine, very low melting points, and then argon, which is just a noble gas that doesn't really react. So using our knowledge of melting points of different structures from before, the melting points increase because of, let's say we're going through metals, then increase sharply, they peak sharply, and then they decrease. So we look at period 3 to showcase the trend, right? For sodium, magnesium, and aluminium. For sodium, magnesium, and aluminium, right? These all have metallic structures. So melting points and boiling points increase from sodium to aluminium. And this is because each element donates one more electron to the sea of free electrons. And on top of that, the nuclear charge also increases. So from sodium to magnesium to aluminium, the nuclear charge increases. So you're going from +1 positive charge to +3, and also they donate more electrons to the sea of delocalized electrons. So there's a stronger electrostatic attraction. So the electrostatic attraction becomes greater, so the melting point rises, and also there's more electrons available. So more electrons available, greater nuclear charge, and there's a greater electrostatic attraction between the nucleus and the electrons. So the melting point would increase as you go from group 1 to group 3 because you're donating more electrons as you go across the period. So not group 1 to group 3, as you're going from it is group 1 to group 3. From group 1 to group 3, sodium, magnesium to aluminium, donating more electrons, and nuclear charge increases, greater electrostatic attraction. All right. Silicon has the highest melting point. This is because it has the giant covalent structure. And to melt silicon, you must break the strong covalent bonds, which requires a lot of energy, and therefore it has just the highest melting point out of all of the elements in period 3. And you can see these group 4, even carbon, as I said before, that can form diamond, and it has forms graphite, but like as I said before, giant covalent structures require a lot of energy to break. Then you go down to phosphorus, silicon, chlorine, argon, and these elements are simple molecular, and they're held by together by van der Waals forces, and the van der Waals forces do matter. They do, as you go down, as you go across the period, the what's it called, the melting point will decrease because they form different structures. So depending on the number of the number of van der Waals forces that could possibly be formed. So sulfur has the highest melting point out of the 4 because it exists as molecules of S8. This means it has a lot of electrons per molecule, so it has stronger van der Waals intermolecular forces or van der Waals attractions. By contrast, phosphorus exists as P4 and chlorine exists as CO2. Obviously, argon is noble gas. Sorry, so if we're talking about the melting points across period 3, sodium, magnesium, and aluminium will have metallic bonding, so they would increase, and I've already said they increase as you go across the groups. Silicon, giant covalent bonding, the highest melting point. It requires a lot of energy to break those silicon covalent bonds. Phosphorus, sulfur, chlorine, molecular solids. Sorry, I should remove that there. And then argon, which is an atomic solid, and it exists by itself really, and has the lowest melting point. And that's it. Hopefully the video was helpful, and that's it.